is stereochemistry? It is the branch of chemistry concerned with the three-dimensional aspects of molecules. And this material will be much more understandable if you use your model kits and actually follow along with your model as I do this lecture. So you might want to go ahead and make yourself an ethane molecule, which is just two carbons bonded to each other, and each carbon has 3 hydrogens. So I would pause the video, make the model, and then resume the video and try rotating the molecule. So sigma bonds, which are formed by a head-to-head overlap of hybrid orbitals between these two carbons, they are sp3 orbitals overlapping, those can freely rotate in open chain molecules. So ethane here, this carbon-carbon bond can freely rotate. So this shows what happens after you rotate along that carbon-carbon bond. If we look at this video, this also shows the carbon-carbon bond of the ethane molecule rotating. So here this carbon is staying put, and then we're just rotating the back carbon. And we're actually going to be doing this when we draw Newman projections. This is a view of that same molecule but from the front. So here you're rotating the back carbon, and just notice how the atoms are changing where they are in space. The different arrangements of atoms that result from bond rotation result in conformers. So conformers are just molecules that have a different spatial arrangement of atoms. And they can be represented either as the sawhorse representation shown here or the Newman projection. And the Newman projection is the one that we're going to be using. We're not really going to be using the sawhorse representation. But see if you can see how the representations correlate to the molecule. So the molecule here is ethane. So this would be the carbon that corresponds to this carbon, and it has the 3 green hydrogens bonded to it, and then this would be the other carbon, which corresponds to that carbon, and it has the 3 red hydrogens. Now the Newman projection is a little bit more confusing to understand. So the Newman projection, which I'll show you how to draw on the next slide, you're looking down that carbon-carbon bond. And so this would be the front carbon, which is represented by this intersection of 3 lines, and then the 3 hydrogens that are in green are bonded to it. And then the back carbon, which is hard to even see from this view, is represented by a circle behind that, and then the hydrogens in red are attached to it. So the way you draw a Newman projection is the front carbon is essentially 3 lines intersecting, and then the back carbon is a circle with bonds coming off of it. So this is how your Newman projection will look. This would be the front carbon, and this would be the back carbon. So my approach to drawing these is first I draw the circle, and then I draw my 3 lines in the front, and then my 3 sticks hanging off the back circle. So this would be my front carbon, the big circle is my back carbon, and then I would have various things hanging off of those carbons depending upon what molecule it is. So if it was ethane, they would all be hydrogens. And let's take a look at that video again. So here we see the Newman projection, and we could stop it at various stages and then draw the corresponding conformer. So let's practice drawing Newman projections. Can you draw this molecule shown here as a Newman projection? And you're looking down the bond as I've illustrated. So you're looking down this bond. So this would be the front carbon, and this would be the back carbon. So first I'm going to draw my circle and with my 3 lines, and then my lines on the back. So the front carbon would be this carbon here, and what's hanging off of it? Well, if you're looking down that bond, the bromine is on the right, the hydrogen's on the left, and the other hydrogen's pointing straight up. And then if you look at the carbon in the back, represented by this circle, the bromine looks like it's on the left, the hydrogen looks like it's on the right, and then the other hydrogen would be pointing straight down. And I recommend making this molecule and looking at it, and you can see how the things that are wedged like this look like they're on the right side, and the things that are hatched like this look like they're on the left side. Torsional strain is defined as the strain in a molecule caused by electron repulsion between eclipsed bonds. Staggered conformation is the most stable, and the eclipsed conformation is the least stable, and I'll show you in a minute what the staggered and eclipsed conformations look like. So in the staggered conformation, the hydrogen atoms in ethane are spaced away as far as possible. So notice here the angle between these two hydrogens is 60 degrees, and between the hydrogen in red and blue here is 180 degrees. Now you could rotate the carbon-carbon bond and have the hydrogens exactly line up with each other. And that would be called the eclipsed conformation. Now in the eclipsed conformation there is torsional strain because the electrons in the carbon-hydrogen bonds that are eclipsing one another will repel each other. So between these two, the lower energy conformer is the staggered conformer, and the eclipsed conformer is the higher energy conformer. Now we can reflect the different energy values for the eclipsed and staggered conformation using a graph of potential energy versus bond rotation. So if we start over here, the x-axis shows the amount of bond rotation. So if we start at our starting point that we're just designating 0, we could have started with any conformer. This would be the eclipsed conformer shown here. Notice how the hydrogens are right on top of each other. Now if we rotate counterclockwise 60 degrees, we get to this conformer. Now this is the staggered conformer. Then if we rotate another 60 degrees, we get to the next eclipsed conformer. So this is eclipsed and this is eclipsed. Then if we rotate another 60 degrees clockwise, we get to a staggered conformer. Then if we keep rotating, it alternates back and forth until we end up where we started. So notice we're always alternating eclipsed, staggered. And the staggered conformers are the valleys. That's because they are the lower energy conformers, and the eclipsed conformers are the peaks. Now for ethane, the difference between the eclipsed and the staggered conformer is 12 kilojoules per mole. That means it takes 12 kilojoules of energy to move from the staggered conformer to the eclipsed conformer. So ethane is the simplest example, but we're going to go on and look at other alkanes. So if we look at propane, shown here, we can draw the Newman projection looking down this bond. So this carbon would be your carbon shown here. So that carbon is this carbon. And if we're looking down that bond, then we would have the green hydrogens on the right and the left. So here are my hydrogens on the right and the left. And then my methyl would be pointing straight up. So this methyl group is pointing straight up. And then the back carbon, which is represented by the circle, so The circle in the back is the back carbon, and it has the 3 blue hydrogens hanging off of it. So there are my blue hydrogens, and they're represented here. So if we were to rotate, this would be the staggered conformation. If we were to rotate the back carbon 60 degrees clockwise, we would get to the eclipsed conformer. So now that has the hydrogens eclipsing each other, and it has a hydrogen eclipsing with a CH3 group. And these values give you the relative energy penalty for those eclipsing interactions. As we move on to larger alkanes, the conformational situation can get more complex, and we can look at conformations along every single different carbon-carbon bond. And it turns out that with staggered conformations, they don't all have the same energy, and not all eclipsed conformations have the same energy. The anti-conformation, the lowest energy and best conformation, in which it's a staggered conformation and the largest substituents are as far apart as possible, 180 degrees apart. So if we look at butane, so here's butane, and we're going to look down the carbon 2, carbon 3 bond. So we're going to look down this bond here. So first of all, do you understand how the Newman projection corresponds to that? So this carbon is represented by the intersection of those 3 lines. The hydrogens in blue here are shown here. The methyl group up here would be pointing straight up. Then the carbon behind that carbon is represented by the circle in the back here. And what does it have bonded to it? It has the hydrogens shown in green, those 2, and then it also has a methyl pointing down. So here the biggest groups, which are the methyl groups, they're bigger than the hydrogens, are 180 degrees apart. And that is called the anti-conformation. It's a type of the staggered conformation, and it's the lowest energy one. So this is the most preferred conformation. Now if we rotate 60 degrees, so we're going to keep the front carbon still and just rotate the back carbon, then we get to an eclipsed conformation where now the methyl and the hydrogen are eclipsed here, as are the methyl and hydrogen there. And then you have eclipsing interaction with those hydrogens. Now there's another type of conformation, staggered conformation, called the gauche conformation. And in this, the large groups are 60 degrees apart. So if we take our conformer here and we rotate another 60 degrees, just the back carbon, then we get to this conformer. Now the large groups are 60 degrees apart. That's not as good as having them 180 degrees apart. What's going to happen is we're going to get steric strain, and steric strain refers to atoms bumping into each other. Their electron clouds are getting close enough that they actually start to bump into each other and repel. So here, if we compare the gauche conformation with the eclipsed, we can see it has a lesser energy penalty, so it's better than the eclipse, but it's not as good as the anti. So this would be all the Newman projections you could draw by rotating 60 degrees. So here we're just rotating the back carbon. So if we started at this point, and I could have arbitrarily chosen any point to start at. So if we start with the eclipse and then we rotate 60 degrees, we get to this gauche conformation where the large groups are 60 degrees apart. Then when we rotate again another 60 degrees, we get to this eclipsed. Then when we rotate again, we get to this anti. Now remember, we're always alternating between eclipsed and staggered, eclipse and staggered. Anti and gauche are just 2 different types of staggered conformations. This is the best one. This is where those big groups are as far apart as possible. Then we go back to eclipsed. Then we go back to a gauche staggered conformation, and then we're back to where we started. Now, among the eclipsed, the one that has the highest energy would be this eclipsed because the two largest groups are right on top of each other. And here we could actually do a plot of potential energy versus rotation for all of those conformers. So in butane, the anti, looking down the C2C3 bond, the anti-conformer is the lowest in energy. Then if we rotate that back carbon 60 degrees, we get to an eclipsed conformer, which is going to be one of the peaks. Then we get back down to a staggered conformer, which will be a valley. But notice this staggered conformer, the gauche conformer, is higher in energy than the anti. That's because there's some steric strain. Those methyl groups are a little closer than they really want to be. Then we rotate again, we get back to an eclipsed. Now notice this peak is higher than that peak. That's because the eclipsing large groups has a higher energy penalty than the methyl eclipsing with the teeny tiny hydrogen. And then we rotate again, we get back to the gauche conformer. And then we rotate again, we get back to an eclipsed conformer. So these two eclipses have the same energy, because if you look at what's eclipsed, it's a methyl and a hydrogen, two of those, and then two hydrogens. That's the same type of eclipsing interactions on that one. And then if we rotate again, we're back to where we started. So what are the types of strain in these interactions? When we have hydrogens eclipsing each other, it's just torsional strain, because hydrogens are so tiny, they really aren't going to have any steric strain. With a hydrogen eclipsed with a methyl, that's also mostly torsional strain. Now, when we have the methyl groups eclipsing each other, we get both torsional and steric strain. And then in the gauche staggered, we get only steric strain. So the torsional strain is only in the eclipsed interactions, but the steric strain can be in both depending on what groups are eclipsed. And sometimes torsional strain is called eclipsing strain. Now I can show you how, if you had your model, you could actually rotate it and see the difference between the eclipsed and the staggered. So what this shows right here is the staggered. And then if I rotate it, now I have the eclipsed. And now I have the staggered. Rotate again, the eclipsed, staggered, eclipsed, staggered, eclipsed, staggered, eclipsed, staggered, and so forth. Now let's try an example. So we want to draw the Newman projections for 2-bromobutane looking down the C2-C3 bond. And you want to label each Newman projection as staggered anti, staggered gauche, or eclipsed. So I've started you off here with the Newman projection. So this is your starting point. And with this, notice that this is eclipsed. The methyls are eclipsing each other, and then the bromine and the hydrogen and the two hydrogens are eclipsing each other. So first of all, 2-bromobutane. So butane has 1, 2, 3, 4 carbons, and then bromine would be a carbon 2. Now if I'm looking down that C2 bond, if I wanted to draw this kind of like a sawhorse projection, I would have my H's here and my methyl up, and then this methyl would be up, and I'd have a bromine here and a hydrogen there. So this sawhorse projection corresponds to that Newman projection. So when you do this, you want to keep the front carbon still and just rotate the back carbon 60 degrees. So you can just keep the front carbon the same for all of these, and you're just going to change what's happening with the back carbon. Okay, so if I rotate this 60 degrees, then the methyl in blue will move over here 60 degrees. The methyl in red, it's on the front carbon, so it's just going to stay put in all of these. So I'm not moving the front carbon. And my hydrogens on the front carbon are also going to stay put, because I'm just rotating the back carbon. Okay, so the methyl in blue is going to move over 60 degrees, and then the bromine would also move over 60 degrees, and then the hydrogen would move over 60 degrees. So now that's the next conformer. Now let's rotate another 60 degrees. So when you're drawing the eclipsed conformers, I usually just draw the bonds a little bit to the side of the front bonds. They're right on top of each other, but visually you want to draw them just a little bit askew. So now the bromine will be here, the methyl in blue will be here, and your hydrogen will be up here. Now rotate again. Now we're going to go to a staggered conformer, because we're always alternating between eclipsed and staggered. So now the methyl is going to be down here, the hydrogen will be over on the right, and the bromine will be up on the left. Now I rotate again to the eclipsed conformer. Now the bromine is here at the top, the methyl is over here, and the hydrogen is here. And then finally, I'm going to go back to one more staggered. And here the bromine will now be over on the right, the methyl will be on the left, and the hydrogen is here. So now we have all of the Newman projections drawn, so we want to label each as staggered, anti-staggered, Gauss, or eclipsed. So the eclipsed ones would be this, this, and this. And then the staggered would be this, this, and this. Now with the staggered anti versus staggered Gauss, the anti is the one which places the two biggest groups on the front and back carbon 180 degrees apart. So you may now be wondering, well, what's bigger, the methyl or the bromine? Because that makes a difference. Well, the size of the methyl group is going to be bigger than the size of the bromine group. So the anti will be the one in which the methyl groups are 180 degrees apart, which will be this conformer. And then these would be the gauche. Another question I could ask is, can you draw the Newman projections and then plot them on an energy diagram? I'm actually going to use a different molecule here. We're going to use 2,3-bromoethane. So let's first draw a Newman projection to start at 0, and I will, in questions, start you off with a particular projection. So let me start off with this one. So this would be the anti-projection. And so that's going to be the lowest energy conformer. Then if I rotate 60 degrees, I'm keeping the front carbon the same. Then my bromine goes over here, and my H is moved there. So now I have an eclipsed, so that's going to be higher in energy. So let's put that up here. And then if I rotate again, I'm going to get to a conformer where, again, the front carbon's the same, but now the bromine's over here. So now this is staggered, but it's gauche. So it's going to be a valley, but it's going to be a little bit higher energy than the anti. And then if I go to another 60-degree rotation, then I get to another eclipsed. But notice with this eclipsed that the bromines, the larger atoms, are eclipsing. So this is going to be actually a little bit higher in energy than the 60-degree eclipsed conformer. Then I rotate again, just the back carbon. I get back to a staggered. This is a staggered gauche, so it's going to be of equal energy as the one at 120. Then I rotate again, and I'm going to go back to an eclipsed. And this eclipsed is about the same as the eclipsed at 60 degrees, so energy level needs to be the same as the one at 60, so I'm going to kind of right on top of that there. And then 360, we would be back to what we started with. So we have our various energy levels. So now I'm just going to connect this with a curve. And this would be my anti-staggered. This is my gauche. And then this would be my eclipsed, all three eclipsed. But the one here is the highest in energy because it has the larger groups eclipsing. In summary, in Chapter 3, we learned about functional groups. We talked about alkanes being a class of saturated hydrocarbons, meaning they just have single carbon-carbon bonds. They're relatively unreactive. And constitutional isomers are compounds that have the same formula but different structures because their atoms are connected differently. Rotation's possible around sigma bonds, and therefore alkanes can exist in a large number of rapidly interconverting conformations. Newman projections are useful in visualizing the spatial arrangement of the atoms as a consequence of bond rotation, and the staggered conformers are more stable than the eclipsed conformers, and the staggered anti is the most stable, where that term is applicable.